We find several solid figures in our homes like a chair, a table, a cup, a glass, etc. All these solid substances have their unique properties. For different applications, we require solids of different properties. These properties depend upon the nature of constituent particles of the solids. Is air a solid, or a liquid, or a gas? The air is a gas as it can flow from one place to the other. Let us learn the different possible arrangements of particles in solids in this module. After reviewing this digital content, we will be able to discuss general characteristics of solids, differentiate amorphous and crystalline solids, classify crystalline solids on the basis of the nature of binding forces, give definitions of crystal lattice and unit cell, find number of atoms in a unit cell, describe voids and close-packed structures, relate the density of a substance with its unit cell properties, explain the imperfections in solids, understand the electrical and magnetic properties of solid. The solids are distinguished by their incompressibility, rigidity, and mechanical strength. For example, when we press a book, it doesn't change its shape. This represents that the book is incompressible. The molecules, atoms or ions in the solids are closely packed. That is, they are held together by strong forces and cannot move at random. Characteristics of solids. Some of the characteristic properties of solids are as follows. They have definite volume and shape. They have slow diffusion rate. Their vapor pressure is low. Their intermolecular distances are short. Their intermolecular forces are strong. They are rigid and incompressible. Examples: sodium chloride, sugar, copper, silver, etc. Solids can be categorized as crystalline solids and amorphous solids, depending upon the nature of the order present in the arrangement of the particles. Characteristics of crystalline solids. The units of a crystalline solid are arranged in an ordered pattern. These have long-range order. These are anisotropic in nature. Note: anisotropic in nature means that the solid is dependent on directions. For example, a light ray coming from a polarizer shows anisotropic nature. Examples: diamond and table salt, etc. Characteristics of amorphous solids. The units of an amorphous solid or non-crystalline solid are arranged in an irregular manner. They do not have a sharp melting point. These solids have short-range order. These are isotropic in nature. Note: isotropic means that the properties of a solid are independent of the directions. For example, coal, glass. The major differences between crystalline and amorphous solids are given in the table. The crystalline solids are classified into 4 categories: molecular solids, ionic solids, metallic solids, and covalent solids, depending on the nature of intermolecular forces. Let us first discuss the molecular solids. Molecular solids. These are further divided into 3 categories: non-polar molecular solids, polar molecular solids, and hydrogen-bonded molecular solids. Non-polar molecular solids. The primary interactions between non-polar molecules are London dispersion forces. These solids are usually in liquid or gaseous state at standard room temperature and pressure. These solids are soft and non-conductors of electricity. Examples: iodine, helium. Polar molecular solids. The molecules are held together by relatively stronger dipole-dipole interactions. Dipole. An electric dipole is defined as the separation of positive and negative charges. These are soft and non-conductors of electricity. Most of these solids are gases or liquids under standard room temperature and pressure. Examples: solid SO2 and solid NH3. Hydrogen-bonded molecular solids. The molecules of such solids contain polar covalent bonds between H and F, O or N atoms. Strong hydrogen bonding binds the molecules of such solids. They are non-conductors of electricity. Generally, they are volatile liquids or soft solids under standard room temperature and pressure. Example: ice. The next is ionic solids. The constituents of ionic solids are cations and anions. These are held together by electrostatic forces of attraction. They are hard, brittle, and bad conductors of electricity. Examples: NaCl, MgO. Metallic solids. Their constituents are cations and delocalized electrons. These are held together by metallic bonds. They are lustrous, ductile, malleable, and are very good conductors of heat and electricity. Luster. The property of metals due to which they shine. Ductile. A metal is said to be ductile if it can be molded into a wire. Malleable. A metal is said to be malleable if it can be molded into a sheet. Examples: NaAl. Covalent solids. The constituent particles are atoms. These particles are held together by covalent bonds. These are non-conductors of electricity. Examples: diamond, silicon carbide. The regular repetition pattern of constituent particles is the main characteristic of a crystalline solid. This pattern is also known as crystal lattice. Let us know the characteristics of crystal lattice. Some of the characteristics are given below. Each constituent particle is represented by one point in a crystal lattice. These points are known as lattice point or lattice site. Lattice points in a crystal lattice are joined together by straight lines. By joining the lattice points with straight lines, the geometry of the crystal lattice is formed. Here, the geometry is of square shape. The smallest portion of a crystal lattice is known as a unit cell. A unit cell is a building block of a crystal lattice. For example, a brick is considered as a building block of a wall. Parameters of a unit cell. A unit cell is characterized by 6 parameters. Its parameters include 3 edges, A, B, and C, and angles between them. The dimensions along the edges of a unit cell are length B, breadth A, and height C. The volume of a unit cell is given by length into breadth into height, or B into A into C. The angle between B and C is represented by alpha, between A and C by beta, and between A and B by gamma. Unit cells are categorized into 2 groups: primitive unit cells and centered unit cells. Primitive unit cell. In a unit cell, when particles are present only at the corners, It is known as the primitive unit cell. Centered unit cell. In a unit cell, when particles are present at other positions in addition to those at corners, it is known as the centered unit cell. There are three types of centered unit cell: body-centered unit cell, face-centered unit cell, end-centered unit cell. Let's discuss them in detail. Body-centered unit cell. In this type of unit cell, one constituent particle lies at the center of the body of a unit cell in addition to the particles lying at the corners. It is called body-centered unit cell. Face-centered unit cell. In this type of unit cell, one constituent particle lies at the center of each face besides the particles lying at the corner. It is known as face-centered unit cells. End-centered unit cell. In this type of unit cell, one constituent particle lies at the center of any two opposite faces besides the particles lying at the corners. It is known as end-centered unit cell. It is also known as base-centered unit cell. There are 7 types of primitive unit cells. These are cubic, tetragonal, orthorhombic, monoclinic, hexagonal, rhombohedral or trigonal and triclinic. There are 14 possible crystal lattices which are commonly known as Bravais lattices. Cubic lattice. There are 3 types of lattice possible for cubic lattice. These are primitive, body-centered and face-centered lattices. In these lattices, all sides are of equal length and the angles between their faces are of 90 degrees. Tetragonal lattice. Primitive and body-centered unit cells are the 2 types of tetragonal lattices. In these lattices, one side is different in length and angles between the faces are equal to 90 degrees. Orthorhombic lattice. There are 4 different types of orthorhombic lattice. These are primitive, end-centered, body-centered and face-centered. These lattices have unequal sides and the angles between their faces are equal to 90 degrees. Monoclinic lattice. There are 2 types of monoclinic lattices. These are primitive and end-centered. These lattices have unequal sides and 2 faces have angles other than 90 degrees. Hexagonal lattice. Only one type of hexagonal lattice is possible. One side of this lattice is different in length to the other 2 sides and the angles on 2 of its faces are 60 degrees. Rhombohedral lattice. It is of one type only. It has all sides equal and angles on 2 of its faces are less than 90 degrees. Triclinic lattice. Like hexagonal and rhombohedral lattices, triclinic lattice has only one type of lattice. It has unequal sides and none of the angles between faces are equal to 90 degrees. Let us now learn to calculate the number of atoms in the different cubic unit cell. Simple cubic or primitive unit cell. In primitive unit cell, atoms are present at 8 corners and every corner is shared by 8 adjacent unit cells. Therefore, only 1/8 of an atom belongs to a particular unit cell. Thus, the total number of atoms in a primitive unit cell is 8 into 1/8 equal to 1. Body-centered cubic unit cell. In a body-centered cubic unit cell, there are 8 atoms present at each corner and 1 atom present at the center of the body. Thus, the total number of atoms in one body-centered unit cell is 2. Face-centered cubic unit cell. In a face-centered cubic unit cell, there are 8 atoms present at each corner and 6 atoms are present at each face. Thus, the total number of atoms in one face-centered cubic unit cell is 4. In solids, the particles are closely packed, leaving minimum vacant space. Consider the particles to be identical hard spheres. Let's understand it in 3 steps. Close packing in one dimension. Here, each sphere is in contact with its 2 nearest neighbors. So, its coordination number is 2. Note: the number of nearest neighbors of an atom is called its coordination number. Close packing in 2 dimensions. This type of packing is generated by stacking the rows of close packed structure. It can be done in following ways. Cubic close packed structure. Hexagonal close packed structure. Cubic close packed structure. As we can see that only one layer, A, is repeated, so this type of arrangement is called AAAA type of arrangement. CCP is found in metals like copper, silver, etc. Hexagonal close packed structure. As we can see that 2 layers, A and B, are stacked together. So this type of arrangement is called ABAB type of arrangement. HCP is found in metals such as magnesium, zinc, etc. Close packing in 3 dimensions. This type of packing is generated by stacking 2-dimensional layers one above the other in a close packed structure. The empty space left after the packing of a close packed structure is known as a void. 2 types of voids are formed in cubic closed packed and hexagonal closed packed structures. These are tetrahedral voids and octahedral voids. In AAA type of arrangement of particles, the space between the particles is known as tetrahedral voids because a tetrahedron is formed. When we place another layer on the tetrahedral voids, the space, the voids created are known as octahedral voids because an octahedron is formed. Note: the number of tetrahedral voids formed is twice the number of octahedral voids in the close packing of atoms in CCP and HCP structures. Let the number of close packed spheres be n. Therefore, the number of octahedral voids is equal to n. Thus, the number of tetrahedral voids is equal to 2n. Packing efficiency. It is defined as a measure of the available space being occupied by atoms. Steps to calculate packing efficiency of a crystal structure. First, find the volume of the unit cell. Second, find the number of atoms per unit cell. Third, find the volume of a single atom. Fourth, multiply the volume of a single atom by the number of atoms. Fifth, divide this multiplication result by the volume of the unit cell. Convert the result into percentage if required. Formula for calculating packing efficiency is given as packing fraction in percentage is equal to volume occupied by spheres present in a unit cell divided by total volume of unit cell multiplied by 100. Let's calculate the packing efficiency of HCP and CCP structures. Let the side of a unit cell be A and diagonal be PR, B, B. Now in triangle PQR, PQ is perpendicular, SR is base and PR is diagonal. By Pythagorean theorem, PR square is equal to PS square plus SR square. This implies B square is equal to A square plus A square, which gives 2A square, or B is equal to A square root 2. Let R be the radius of sphere. Therefore, B is equal to 4R. Thus, B is equal to 4R equal to A root 2. This implies A will be equal to 2 times R square root 2. Let it be equation 1. Now the volume of a cube is equal to side cube equal to A cube. After substituting the value of A from equation 1, we get volume of cube is equal to 2R root 2 cube. Let it be equation 2. Now, volume of one sphere is 4 by 3 pi R cube. Since one unit cell of CCP or HCP contains 4 atoms, that is, 4 spheres. Therefore, volume of 4 atoms is equal to 4 into 4 by 3 pi R cube. Let it be equation 3. Now, packing efficiency can be calculated using the formula. By solving this further, we get 74% as its packing efficiency. Similarly, we can find the packing efficiency of body-centered cubic lattice, which is calculated as 68%, and simple cubic lattice, which is found out to be 52.4. Let the edge of a unit cell is A. The density of unit cell is D. Molar mass of unit cell is M. Number of atoms present in unit cell is Z. Mass of each atoms present in unit cell is M. So, mass of one atom present in unit cell is M by Na. Therefore, mass of unit cell is equal to number of atoms present in unit cell times mass of one atom. This implies mass of unit cell is Z into M, which implies Z into M by Na. We know that density is equal to mass of substance by volume. Therefore, density D of unit cell is equal to mass of unit cell by volume of unit cell. The density is found out to be Z into M by A cube into Na. Here, Na is the Avogadro constant or number. An irregularity in the arrangement of particles of a solid is called crystal defect or imperfection in solids. Line defects and point defects are the two types of crystal defects found in solids. Line defects. The defects arising due to the presence of irregular particles across the row of a lattice point are referred to as line defects. Point defects. The defects arising due to the irregularities of particles around the single lattice point are called point defects. Point defects are in general classified as stoichiometric, non-stoichiometric and impurity defects. Stoichiometric defects. They do not change the stoichiometry of the solid. These defects exist in ionic and non-ionic solids. In case of non-ionic solids, two types of defects are commonly observed: vacancy defect and interstitial defect. Vacancy defect. When some of the lattice sites are vacant or empty, the crystal is said to have a vacancy defect. In this defect, the density of the substance decreases. This defect is observed when a substance is heated. Interstitial defect. When some of the particles occupy an interstitial site, the crystal is said to have interstitial defect. Defects in ionic solids. Frenkel defect. The ratio of cations and anions remains the same in this defect. An ion missing from the lattice occupies an interstitial void. The electrical neutrality and stoichiometry of the crystal remains the same. In this defect, density is not affected. This type of defect is found in AgCl and AgBr, etc. Frenkel defect is also called dislocation defect. Schottky defect. Equal number of cations and anions are missing from lattice sides. Electrical neutrality of the crystal is maintained. It decreases the density of the material. Schottky defects are found in NaCl, KCl, KBr, etc. Non-stoichiometric defects are of two types: metal excess defect and metal deficiency defect. The metal excess defect is found to be of following two types: metal excess defect due to anionic vacancies, metal excess defect due to the presence of extra cations at interstitial sites. Metal excess defect due to anionic vacancies. When the crystals of KCl are heated in an atmosphere of potassium vapor, the potassium atoms are deposited on the surface of crystal. The loss of electrons makes potassium atoms to form K+ ions. These released electrons occupy anionic sites are known as F centers. The excess of potassium makes KCl crystals violet. Metal excess defect due to the presence of extra cations. The metal excess defect may also be observed due to the presence of extra cations at interstitial sites. When white-colored, zinc oxide is heated, some oxygen is released and turns yellow. The remaining extra zinc ions occupy the interstitial sites of the lattice, thereby developing the metal excess defect. Metal deficiency defect. The metal deficiency defect is found when a metal ion is lost from their lattice site. In such cases, in order to maintain the electrical neutrality of lattice crystal, some of the ions acquire extra positive charge by losing electrons and move to the higher oxidation state. Impurity defect. This defect arises when the cations leave their sites and foreign cations occupy the vacant site of the crystal lattice. Example: when molten sodium chloride containing a little amount of strontium chloride is crystallized, some of the sites of sodium ions are occupied by strontium 2+ ions. Each strontium 2+ ion replaces two sodium plus ions. It occupies the site of one ion and the other site remains vacant. The cationic vacancies thus produced are equal in number to that of strontium 2+ ions. On the basis of magnitude of range of conductivities, that is, from 10⁻⁻20 to 10⁻⁷ ohm, inverse meter inverse, solids are broadly classified as conductors, insulators, and semiconductors. Conductors. The solids with conductivities in the range 10⁻⁴ to 10⁻⁷ ohm, inverse meter inverse, are classified as conductors. For example, metals are the good conductors of electricity. Insulator. The solids with conductivities in the range 10⁻⁻20 to 10⁻⁻10 ohm, inverse meter inverse, are considered as insulators. For example, rubber, wood, etc. Semiconductor. The solids with intermediate range of conductivities, that is, from 10⁻⁻6 to 10⁻⁴ ohm, inverse meter inverse, are classified as semiconductors. For example, silicon and germanium. Now let us discuss the conduction of electricity in these substances. Conduction of electricity in metals. When partially filled energy levels or valence band are very close or overlapped with unoccupied energy level or conduction band, electrons can easily flow between them on the application of electric field. This flow of unpaired electrons from valence band to conduction band makes metal good conductor of electricity. Conduction of electricity in insulators. In insulators, the difference in energy between occupied energy level and unoccupied energy level is higher, due to which electrons cannot flow from occupied energy band to the unoccupied energy band. This makes insulators poor conductors of electricity. Conduction of electricity in semiconductors. In semiconductors like silicon and germanium, the energy gap between valence band and conduction band is small, such that electrons are capable of jumping from filled band to empty band when an electric field is applied to it. Because of lower gap between valence band and conduction band, semiconductors show the conduction of electricity. The conduction of electricity in semiconductors generally increases with increase in temperature. Doping. The conductivity of these semiconductors is very low for practical purposes. Their conductivity is increased by adding an appropriate amount of suitable impurity. This process of adding impurity to increase the conductivity of semiconductors is called as doping. N-type semiconductors. Silicon and germanium are doped with electron-rich impurities like the elements of group 5 of the periodic table, for example, phosphorus, to increase their electrical conductivity. The semiconductors so formed are called N-type semiconductors. P-type semiconductors. The electrical conductivity of silicon or germanium is often doped with elements of group 3 of the periodic table, like boron, aluminium or gallium. The semiconductors so formed are called P-type semiconductors. Applications of N-type and P-type semiconductors. The N-type and P-type semiconductors are used in making electronic components. They are used in diodes, which is the combination of N-type and P-type semiconductors. They are used in transistors to amplify radio and audio signals. Substances can be classified into 5 types on the basis of their magnetic properties. These are paramagnetic, diamagnetic, ferromagnetic, antiferromagnetic, ferrimagnetic. Paramagnetism. The substances which are slightly attracted on the application of the magnetic field and do not retain the magnetic property after removal of magnetic field are called paramagnetic substances, and the phenomenon is known as paramagnetism. For example, O2, Cu2+, Fe3+, etc. Dimagnetism. Dimagnetic substances are just opposite to that of paramagnetic substances. The substances which are slightly repelled by magnetic field are called dimagnetic substances, and the phenomenon is known as dimagnetism. For example, H2O, NaCl, C6H6, etc. These substances are slightly magnetized when put under magnetic field, but in opposite direction. Ferromagnetism. The substances which are strongly attracted by magnetic field are called ferromagnetic substances, and the phenomenon is known as ferromagnetism. For example, cobalt, nickel, iron, gadolinium, chromium oxide, etc. These substances can also be permanently magnetized. Antiferromagnetism. The substances in which the domain structure are similar to that of ferromagnetic substances but are oriented oppositely, which cancel the magnetic effect, are termed as antiferromagnetic substances, and this property is referred as antiferromagnetism. For example, MnO. Ferrimagnetism. The substances which are slightly attracted in the magnetic field's direction and in which domains are grouped in parallel and anti-parallel direction in unequal number are termed as ferrimagnetic substances, and this property is referred as ferrimagnetism. For example, magnetite, ferrite, etc. Let us summarize the main points covered in this digital content. The solids are distinguished by their incompressibility, rigidity, and mechanical strength. The smallest portion of a crystal lattice is known as a unit cell. Unit cells are categorized into two groups: primitive unit cells and centered unit cells. There are 14 possible crystal lattices, which are commonly known as Bravais lattices. The empty space left after the packing of a close-packed structure is known as a void. Packing efficiency is defined as a measure of the available space being occupied by atoms. An irregularity in the arrangement of particles of a solid is called crystal defect or imperfection in solids. The defects arising due to the presence of irregular particles across the row of a lattice point are referred to as line defects. The defects arising due to the irregularities of particles around the single lattice point are called point defects. Stoichiometric defects are vacancy defect, interstitial defect, Frenkel defect, Schottky defect. Non-stoichiometric defects are metal excess defect, metal deficiency defect, and impurity defect. Types of substances on the basis of electrical properties: conductors, insulators, semiconductors. Types of semiconductors are N-type, P-type. Type of substances on the basis of magnetic properties: paramagnetic, diamagnetic, ferromagnetic, antiferromagnetic, and ferrimagnetic.